Hey, okay, we're almost at the end. This is the very last video lecture, and it's an exam review. So I should first tell you that you have practice exams posted underneath all the video lectures in that block on our As You Learn site. So make sure that you take advantage of that. And without further ado, let me get along to the exam review. So, what you'll be given on the exam is an equation sheet. Okay, so you're not to make your own equation sheet, you're to use mine. The equation sheet is the same one that you received for the midterm, and it's in the top block of As You Learn, and it's very cleverly entitled Error Analysis Equation Sheet. So that's the one you'll get. You'll also get the Gaussian integral tables, which is table A in the appendix of your book. You'll get table C in the appendix of your book with the probabilities for the linear correlation coefficients, so you'll get that. And you'll get table D in your book, that is the chi-square test probabilities. To bring with you, I want you to bring a calculator and some extra paper. And please, no cell phones or computers during the exam. So with no further ado, let's go back to the very beginning, because this is cumulative, so you'll need to know all the information from the beginning on. So on the very first day of class, we talked about how in your uncertainty, you're going to keep one significant figure, at most two, okay, but one most of the time. And then when you have a number and the reported uncertainty, make sure to match the precision of the uncertainty to the value of your reported number. The only time you really keep two sig figs instead of one sig fig in your uncertainty is when it's going to change the percentage value of your uncertainty if you change it a lot. So if it's, for example, 1.0 plus or minus 0.5 versus 1.0 plus or minus 1.00 plus or minus 0.41. See, that changes the percent uncertainty on that number by 9% or so. And so in that case, it might be all right to keep two sig figs. When you round an uncertainty, when you truncate to one or two sig figs, you're always going to round up. It's scientifically dishonest to round your uncertainty down. Okay? You follow normal rules of rounding for the value, but for your uncertainty, you always round that up. Okay, now, on that error analysis equation sheet that's on the sheet, I only give the general formulas for propagation uncertainty. So the formula for propagating uncertainty through one variable or a multivariable function, I give that, but I don't give all the rules for propagating uncertainty. So if you like to remember those, you're going to have to memorize those yourself. So if you're adding or subtracting, remember you add the square root of the sum of the squares of the absolute uncertainties to find your final uncertainty. Okay? If you're multiplying by a known constant, remember that you preserve the fractional or percent uncertainty. So if you multiply by a known constant, the percent uncertainty stays the same. If you're multiplying or dividing, then it's the square root of the sum of the squares of the fractional uncertainties. Okay, and then that gives you your fractional uncertainty. Be really careful for the formulae that give you a fractional uncertainty that you remember that it's a fractional uncertainty and not an absolute uncertainty. Okay, remember the absolute uncertainties have the same units as the value, right? So it's 1.0 plus or minus 0.1 centimeters, for example. Whereas a fractional uncertainty could be translated over to a percentage, so it's dimensionless. Okay, if you raise something to a power, okay, then you have to multiply that power's number times the fractional uncertainty. And then I give you the general function for one variable function. So if q is q of x, then your uncertainty is the absolute value of the derivative of q with respect to x times that uncertainty in x. So that one is actually given on the sheet, the propagation, the error analysis equation sheet. Anytime you're dealing with angles, remember that the SI unit for angles is radians, not degrees. And so if you're propagating uncertainty through an equation that's got an angle in it, you need to convert that to radians before you do so. And then if you have a multivariable function, then you use this formula here at the bottom of the page. Okay? That one is also given on that error analysis equation sheet. Okay? So that's all Chapter 3, Propagating Uncertainties. Being able to propagate uncertainties is very important, even as you go into Physics 4210, because you'll have all this data that you've taken. You need to calculate a final value, and the final value is calculated by some calculation through your recorded values. So it's very important. Okay, another important thing that you'll need to carry with you is the ability to calculate a mean or an average, and also a standard deviation and a standard deviation of the mean, and what those things mean. So if you take a lot of values and your uncertainties are not systematic errors, but are rather random uncertainties, okay? And that mean or average is of something that is a Gaussian distribution function, that follows a Gaussian distribution function, then taking a mean or an average is useful, okay? So you know how to take an average. Hopefully that's not something I need to review. But a standard deviation is a relatively new idea. So let me remind you that the definition of a standard deviation, which is denoted sigma x, is equal to the square root of 1 over n minus 1, where n is the number of data points, times the sum of the squares of the residuals. Okay? And the residual is the difference between the value and the average value. Now the standard deviation, that is the uncertainty on a single measurement. Okay, the uncertainty on a single measurement. So if you had n values xi, so if you've got n values of some quantity that you've measured, then the standard deviation is the uncertainty on one of those values. However, if you find your average, the uncertainty on your average is the standard deviation of the mean. Okay, so the standard deviation of the mean is your standard deviation divided by the square root of the number of data points that you've got. And that'll be your uncertainty on your average, the standard deviation of the mean. All right, sometimes you want to plot your data out and you want to look at how that data is distributed, okay? So what you do is you divide your data's results into different bins, and you put the data that falls into certain ranges within a bin, okay? And then you want to plot, say, the percentage or the fraction of values that lie in each one of those bins, and that gives you a bar histogram, okay? Bar histograms are useful if all of the bins are the same width. Okay, and then the normalization condition of your bar histogram is that your percentages for the heights of all the values in your bins, those sum to 100%, or if it's a fraction, that the fractions sum to 1. Okay, and that's your normalization condition for your bar histogram. Now, bin histograms are a little different. In a bar histogram, only the height of the bar matters because the bins are all the same width. But in a bin histogram, both the height and the width of the block for each category are important and meaningful. And so for a bin histogram, your normalization condition is that the big f sub k has to sum to equal 1, but big f sub k is equal to little f sub k, which is the height of your bin, times the width of the bin, delta k. Okay, and that's your normalization condition. Bin histograms honestly aren't used as often. Okay, bar histograms are used more often because they're more intuitive. But if you want to make that leap from a histogram to a distribution function, it's important to understand bin histograms. Okay, speaking of distribution functions, if you divide your histogram up into small enough bins, so if you shrink the width of the bin more and more and more, then it starts to look more like a continuous function and yet less like a discrete, blocky type histogram. If you do that, then what you've got is a distribution function versus a histogram. So for a distribution function, we'll call that f sub x. It's got some shape to it, and what the distribution function gives you is the probability that the values lie within certain ranges. So if you integrate your distribution function, say, from a to b, then that'll give you the probability that your value lies between a and b. Okay? If you sum, or if you integrate over all space, then the probability will be 1 because the value has to lie somewhere with 100% probability. If you want your average value from a histogram, then you multiply x times f of x and you integrate over all space, and that'll give you the average value of x. And if you want your variance, which is the square of your standard deviation, then you do your residual, x minus x bar, okay, x bar being here the average, squared, and then multiply that times your distribution function, and that gives you your values. And these map one-to-one onto the equations for bin histograms. Okay, now the first distribution function that we learned about was the Gaussian distribution function. It's also known as the normal distribution function or a bell curve, okay? The Gaussian distribution function is an exponential function. So the Gaussian distribution function equation is given here at the top. So it's 1 over the standard deviation times the square root of 2 pi, and then e to the minus x bar squared divided by 2 sigma squared. Okay, that's your Gaussian distribution function. And it has that characteristic bell curve shape. We talk about what happens within certain confidence intervals. So if it happens between plus or minus 1 standard deviation about the mean, then that's with a 68% probability. If it's plus or minus 2 standard deviations, then that's with a 95% probability that your value will fall within that range. Okay? And we get that from integrating our Gaussian distribution function along those values. Now, the Gaussian distribution function is used so often that they've actually tabulated the value of the Gaussian integrals, okay? And that's given in Table A in your appendix. I do not recommend on your final exam that you try to input and figure out what those integrals actually are in a calculator. Learn to use the table if you haven't already, okay? And practice on some of the problems, all right, that you've already done. Okay, go back through the book, open the book up to the chapter 5 and 6 stuff, and figure out how to use those tables and get it to work for you. The answers to the odd number questions are in the back of the book. Okay, so what this table tells you is up here it'll show you the Gaussian, okay, and then it'll show x minus t sigma to x plus t sigma within that region of the Gaussian function is shaded. Now the values in the tables correspond to the percentages, okay, the percentage probability that x lies within that range, okay. You can figure out if it's outside or inside just by adding or subtracting from 100. Sometimes you have to divide by 2, as you might have seen in some of the homework problems if you're just looking for half that range. So monkey around with it, figure it out. If you're still confused after a little bit, come see me and I'll be happy to help. Okay. We also discussed something called discrepancy. So if you have two measured values and you want to figure out whether or not the difference between those two measured values is significant or not, then you discuss the discrepancy. So let's say that we've looked at two values, P and Q, and we want to know if they're the same or not. So one way to look is to see if the values overlap within their uncertainties, or to look at the discrepancy. Okay? So for the discrepancy, you would subtract P minus Q or Q minus P, and that would give you your discrepancy. And then you compare the discrepancy to the uncertainty on that discrepancy. Okay? If the uncertainty is greater than or equal to the discrepancy probably isn't too significant. So that's more of a sort of qualitative way of looking at the discrepancy. And I do an example here on this slide. If you want to get more quantitative about it, then you can calculate the t-value. Okay? Now, how do you calculate the t-value? So this t-value was also used back here on this slide for the Gaussian distribution function. So for a t-value, you take the difference between the two values, all right, your discrepancy, and then you divide by, for the t-values in the table, the standard deviation of the mean, right? So let's say that you have a mean for male height of 69 inches, right, with a standard deviation of 3 inches, okay? And you wanted to know what the t-value range was. Let's say, what's the probability of being between, say, 60 inches and 78 inches, okay? Well, 60 inches to 78 inches would be 69 minus 60, which would give you 3, and then you divide by your standard deviation. 69 minus 60 gives you 9, and then you divide by your standard deviation, which is 3. So it's 3 standard deviations from the mean on either side. That's how you calculate your t-value for a standard deviation. If you're trying to calculate your t-value for discrepancy, then you calculate your discrepancy, first of all, x1 minus x2, and then you divide by the square root of the sum of the squares of your uncertainties for x1 and x2, and that'll give you the t-value for that discrepancy. Then you find the probability that if a value is that far apart, that it's how likely it is to be that far apart. So its probability outside t sigma is 1 minus the probability that it's inside t sigma, okay? And that gives you that. Then you go to your chart here and see what those probabilities actually are and compare it to a known value. If you're confused by this, just make sure to look back at that lecture that I gave on the Gaussian distribution function, okay? And it'll help you. This is called the t-test, by the way. Okay, chapter 6 was talking about Chauvenet's criterion for data rejection. So yet again, if you have a suspect data point from whatever n measurements that you've got, first you want to calculate your mean and your standard deviation, including the suspect data point within your value. Okay? Then you look at what your t-value is for that suspect data point. So you take the absolute value of the discrepancy between the suspect and the mean, okay, and then divide by the standard deviation. And then you see how likely is it that the data point is that far away. So it's the probability outside t sigma is 1 minus the probability that it's in t sigma. Once you find that probability, then you multiply that probability times the number of data points that you've got, and you look at your little number n. Okay? If n's less than a half, then that doesn't round up to a full data point, and you can reject your data point. And that's Chauvenet's criterion for data rejection. If you're going to reject data, for example, in Physics 4210, you should only reject 1, at most 2 data points from any given set. And that depends on how many data points that you've got. And then if you want to reject your data, you should make sure that it applies Chauvenet's criterion, that Chauvenet's criterion applies to it before you do it. And that's for 4210. Okay, the next chapter in your book is on weighted averages. So it's important to understand that you use a weighted average if the uncertainties on your data points are very different. Okay, so if you are trying to find an average point but the uncertainties on each of your collected data points differ by a lot, then a weighted average might be the way to go. Okay, and the formulae on this page, this slide, give you the weighted average. So it's just, for a weighted average, the sum of the weight times the value divided by the sum of the weights. Okay. And the weights are 1 over your uncertainty squared for each of your values. All right? And then the uncertainty on your weighted average is 1 over the square root of the sum of the weights. So it's pretty straightforward, very formulaic. Another kind of turn the crank type method is linear least squares. So it's important to understand, though, that there's several different computational methods that can be used to find a best fit line. Okay, linear least squares is the most common, but it's not the only one. So what you do in linear least squares is you have a data set. Pardon me. Sorry about that. Okay, so in linear least squares, what you do is you're going to minimize the distance in y from your data point to the line. Okay, so since values are more likely, or just as likely, to fall above and below the line, what you do is you minimize the square of those residuals and not the values themselves. And so it's minimizing the sum of the squares of the residuals. Okay, that's the linear least squares method. Now what this does is, because it's the y residuals that are minimized, it's important to understand that if you have a larger uncertainty in one direction than the other, then you better plot the larger uncertainty on the y-axis. For example, if you plot a whole bunch of data points that have large uncertainties in x, okay, well, linear least squares doesn't minimize the uncertainty this way. It minimizes the uncertainty this way. So your data is going to be screwed up. So you need to flip it so that your y-axis is the one with the largest uncertainty. That gets a lot of people in senior seminar. It's a mistake that a lot of people make, and then they get toasted for it on their talks. Anyway, actually doing linear least squares is no big deal. The formulas are on the sheet. Remember that the fit line is a plus bx, and you can calculate them in a very straightforward way. We've done some practice with it, and the formulas are on the sheet, so it's not hard. The uncertainties, the thing to realize is that it's just the residuals that you're minimizing, but because it takes 2 points to make a line, as opposed to a standard deviation, which is 1 over n minus 1, it's proportional to 1 over n minus 2. And that's just because you need to determine 2 fit constants. Okay? It's also important to understand that as you fit a line, if it's not a linear line, so if it goes up to a quadratic, a plus bx plus cx squared, well, then you'd need at least 3 data points, and so on and so forth. So the more parameters that you have to fit, the more data points you need. Okay, that's Chapter 8. Chapter 9 covers the covariance, which is a measure of whether or not your two values are independent or dependent on one another. So by independent, I mean, for example, position and time in the trajectory of an object can be considered independent as long as you're neglecting air resistance. Okay? So x, for example, or y would be a plus v x final would be equal to x initial plus v initial t plus 1/2 at squared, and x and t or y and t are independent variables. So you measure the position, and that doesn't affect your measurement of the time. Okay, they're independent of one another. Looking at the value for the covariance, the formula is right up there. It's sigma xy. Okay. What it'll tell you is if the measurements are independent, then the covariance will go to 0, right? So in other words, xi minus x bar times yi minus y bar, right? If xi minus x bar is negative, then that doesn't affect whether or not yi minus y bar is positive or negative. They're independent of one another. So that sum over a long time will go to 0. But if x is being more negative makes y more negative, and they're dependent on one another, and then your covariance will tend towards some non-zero number. And so that's why it tells you whether or not they're related. If they are related, then we say that those variables are correlated. Then we talked about the coefficient of linear correlation, and the formula for the coefficient of linear correlation is given here. Okay, if two variables are linearly correlated, then that means that they are well fit by a straight line. And if they're well fit by a straight line, then r will tend to 1 or minus 1. Okay, so the closer it is, the absolute value of r is to 1, the better fit it is by a straight line. You can say how good a fit is by looking for the linear correlation coefficient versus the number of values that you've got. That's table C in your book, okay? And it's important to understand that this gives you the percentage probability that n measurements of two uncorrelated values give a correlation coefficient that large, right? So you can see here, this is the absolute value. So if r is equal to 0, then that would tell us that the things are absolutely not linearly correlated. So no matter what your number of data points are, if r is 0, then it's 100% probability that it's not correlated. Okay. Whereas if it's 1, then it definitely is correlated. So there's a 0% probability that it's not correlated, and that shows up in the chart. Hopefully that's relatively clear. Okay, the next chapters dealt with the binomial and the Poisson distribution functions. Okay, the binomial distribution function gives you the probability that within independent trials, okay, if you call P let's say you're flipping a coin and you say you want heads, okay, and let's say you flip the coin 10 times, then n is 10, those are the number of independent trials. The probability of success, the probability of getting a head would be 1/2, and Q is the probability that you get a tails, which would be 1/2 as well, 1 minus 1/2, okay? And then you can calculate the probability of a certain number of successes. Let's say that you want a head 5 times. So let's say that you want 5 successes in 10 trials. Then you can do that using your binomial distribution function. Out front in the binomial distribution function is the combinatorial function, and that's that n factorial over v factorial times n minus v factorial. Okay? And then remember that we said that for finding the probabilities of independent events, you multiply those probabilities together, which explains the p to the v times the q to the n minus v. All right? Okay. The next distribution function we talked about was the Poisson distribution function, and the Poisson distribution function is for counting experiments like radioactivity experiments. In general, the uncertainty in a counting experiment is the square root of the number of counts. So if you're doing a radiation count for something in a 2-minute count, then the uncertainty, let's say that you measured 10 counts in 2 minutes, then the uncertainty would be square root of 10. For an average for a counting experiment, it's the square root of that average. Okay, so that's important to remember. The Poisson distribution function is given here. It's e to the minus mu to the nu over nu factorial. So let's say that you have an average number of counts for the radioactivity of uranium or whatever in a 2-minute period. That average number would be mu. Okay, and then you get the number of counts that you actually have, and that's v. Okay, so it's the probability that something with an average value of mu actually gets v counts. Okay, so that's your Poisson distribution function. The last chapter in our book concerns the chi-squared test for the goodness of fit to a function. In your book, the focus has been on the distribution functions, the Gaussian, the Poisson, and the binomial distribution function. But you can do a distribution function or a fit to any function. So if you're fitting to some random function f of x, okay, like a linearly squares fit or whatever, and you've collected n data pairs, xy pairs, then your chi-squared is going to be given by this function here, the sum over all your xy pairs, yi minus f of xi divided by the uncertainty there, sigma squared, and that's your chi-squared value. Now, what you would get is, if you did that, the sum would tend towards n, okay? So you want to reduce chi-squared, so that you can compare goodness of fit for any number of variables or any number of data pairs, and that it gives you the same kind of standard all the time. So in fitting programs and spreadsheets, they report the reduced chi-squared, and that's the chi-squared divided by d, the number of degrees of freedom. And the number of degrees of freedom for a fit to a function would be the number of xy pairs n minus the number of constraints. Okay. For a general function, c would be the number of fit constraints. So if you're fitting to a linearly squares line, for example, and the equation is a plus bx, you have to determine a and b from the data. Okay, and so that's 2 constraints. Okay, so if you had 100 data points, data pairs, then you would have a number of degrees of freedom of 98, which is 100 minus 2. Okay, if you're fitting to a distribution function, it's slightly different. Okay, there you're talking about bins instead of number of xy pairs. And so what you do is you calculate the number that you would expect to fall within that bin given the distribution function. Okay, so for example, let's say that you have a Gaussian distribution function and you've broken it up into 4 bins, and the bins are, you know, less than 1 standard deviation, within the mean and 1 standard deviation, above the mean and 1 standard deviation above the mean, and then finally above 1 standard deviation above the mean. So those are your 4 bins. Okay, so in the middle 2 bins, it's a 68% probability that you lie within those bins. So each bin gets 34%. Okay. And then you have the above and below calculation. Okay. So you can calculate what the probability is, how many data points should actually fall within that bin. Okay. And that's the expected E sub k. So that's the expected value for bin k. And then you've got your actual value for bin k, and that's O sub k. Okay. So your chi-squared is the sum of OK minus EK squared, and then divided by EK, which is the number expected for that bin. Okay. And then, of course, the reduced chi-squared you calculate there, the number of degrees of freedom would be the number of fit parameters from that distribution function. So, for example, for the Gaussian distribution function, you have to calculate a mean and a standard deviation. Okay, so that has 2 constraints, and then you would compare that to the number of bins, not the number of data points, the number of bins. So my previous little example with the 4 bins, you'd have 4 bins with 2 constraints for 2 degrees of freedom. And that's what you would divide your chi-squared by to calculate your reduced chi-squared. Okay, this brings us to our last table, which is Appendix D, the probabilities for chi-squared. Okay, and here you're getting the value of the reduced chi-squared and comparing that to the number of degrees of freedom. Okay, and then it's the percentage probability of obtaining a value that's greater than that threshold value that's given in the table. All right, after that, we did a little unit on other physics distribution functions. Here I'm going to say that I'm not expecting you to have memorized any of those distribution functions. Okay, they don't appear on the equation sheet, and I'm not expecting you to memorize them. So if I want you to do anything with, for example, the Maxwell-Boltzmann distribution function, the Fermi-Dirac, or the Bose-Einstein, I'll have to give you those distribution functions. Okay, so don't worry about memorizing distribution functions for those other physics things. I just wanted you to see and get firsthand experience with some of the distribution functions that you might see in physics that weren't covered in a stats book, so you could get a feel for it. So the ones that we talked about were probability densities in quantum mechanics, okay, which is the wave function squared, the Maxwell-Boltzmann distribution function for an ideal gas, the Fermi-Dirac distribution function, that's good for fermions, or spin 1/2 particles, quantum particles, and that works for free electrons within a metal. And then the Bose-Einstein distribution function that works for example, black body radiation. So those are the ones that we covered, other distribution functions in physics. All right, that's it. Just make sure that you go back over your old homeworks, do the practice final exam and the practice midterm if you haven't already, and please feel free to come and see me if you have any questions. Good luck.